Okay guys, let's take a look at today's lesson. We are starting a new unit, yay, 5.1. We're solving trig equations. This unit, actually, we're going to be using the properties and identities that we learned in the last unit. We'll just be using them in a little bit of a different way. In the previous unit, we were looking at solving, so there was an equal, right, with the proofs. There's an equal sign in this, so there were equations. But we were looking at solving the trig equations that were true for all values. You know, the things that we were working on in the last unit, we proved them true for all values of x. It wouldn't matter what value of x we put in there, it would be true. The type of equations we are working on in this unit are conditional equations. They're not necessarily true for all values of x. And I have an example here of cosine x equals 1/2. So if we knew cosine x equals 1/2, and we've dealt with this kind of situation before, here's a graphical representation. So we know there are multiple solutions. All x values don't work, just these particular ones where they're intersected, and we wrote a general solution for that, right? So at pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. And so that's an example of, an equation, this equation right here, that's conditional. It only works for specific values of x, and that's what we'll be working on in this unit. Okay, there's a procedure that we typically use. This would be just for most cases right here, the steps to solve the conditional trig equations. We would use algebra rules and trig identities, the types of things that we worked on in the last unit, to isolate the trig function on one side of the equation. And then we would use our prior knowledge, like unit circle values, that type of thing, to solve for the variable. Many of these we will be doing by hand. There will be some that we'll use a calculator for, but vast majority we would do by hand with unit circle values. Okay, so that is our premise of our first lesson. Are there any questions about anything so far? Okay, we have a few examples to work, so let's turn to that page. So all solutions means to us that we have to write it in general solution form, like we're, plus the 2 pi n or whatever it is happens to be. So let's take a look at our very first one. We have tangent squared minus 3 equals 0. I started with a pretty easy one just to kind of work through the process. I would move the 3 over. I'm going to isolate the tangent. So I have tangent squared equals 3. Then I would square root both sides. Now, there is one classic mistake that happens on this type of problem over and over again. I want to make sure that that doesn't happen to us. So what do you think that classic mistake might be? And it's right at the step where I'm stopping, right up here. So where might that step error be? Yes? Exactly, the plus or minus. If we do not remember to do the plus or minus root 3, then we basically have lost half of our solutions and, half the points on the problem. So we need to be really, really careful, very careful, and make sure that we do the plus or minus. Okay, so let's take a look in unit circle where that might be true, where we might have a positive or negative root 3. I like to go to the principal values. Do you have to? No. You don't have to do principal values. You could do others. But I kind of like staying with the principal values. So tangent would be root 3. Let's see, tangent is sine over cosine, right? So we would need, since the root 3 is whole, we would need the sine to be at the root 3. Right, sine would need to be root 3. So let's think about where that would be. Right here at pi over 3, right? That's where we're at 1/2 root 3 over 2. Okay, so one of the solutions would be at pi over 3. And so we would say x equals pi over 3 plus. What is the standard period for tangent? Do we remember for pi? It's just pi, right? Or 180 degrees. Where I'm using radians for this, so that would be plus pi n. So that would pick up here and here, right? Both of these solutions. But we also have a negative version. And tangent is its principal value, where it's negative is down here. So I'm going to use principal value. And that would be at negative pi over 3. And that's my location is where x is 1/2 and y is negative root 3 over 2. Okay, so that yields the second solution. So x is going to be equal to negative pi over 3 plus pi n. So I have these two solutions. Now I want to make a note here, something that I see errors on I really like to tell you where I mostly see errors so that you don't do them. Some students believe that this is a plus minus, so I can get this solution if I turn this to a plus minus. Okay, that is not the case, right? Because we already know that n could be positive or negative. If I put a plus minus right here, all I'm saying is what we already know, right? N could be positive or negative. So that is not going to get me my second solution. My second solution has to come from the angle measure itself being negative, not this being turned plus minus. Does that make sense? Okay. So there are our solutions for our very first one. Okay, so let's move to the second one. I have 1 plus sine equals 2 cosine squared. I have a mixture of different types. I have a mixture of sine and cosine. So I would prefer to have one trig function to work with rather than two. And I'm seeing a squared and to the first power and a constant. So I want you to be thinking quadratic. That looks very much like a quadratic. We dealt with those in the last unit, remember that? Where we would factor it and to simplify. So I'm going to take the easiest one to change would be the cosine squared, right? I could turn that to 1 minus sine squared. So, and I know you're going to be upset, but you do not have to write reasons on this. If you want to, you certainly can, but it is not a requirement. So we're just going to change the cosine squared to be 1 minus sine squared. Then I'm going to just do some algebra, distribute. So I have 1 plus sine equals 2 minus 2 sine squared. When I factor, I actually prefer for my leading term to be positive. So I would actually move these terms to the left. You certainly don't have to. You can do whatever you want, but I'm going to move these terms to the left. And that would give me, so I have a negative 2, which would give me a positive 2 sine squared x, and then plus sine x. When I move the 2 over, it'll be negative, right? Negative 2 plus 1 is negative 1. So now I'm ready to factor. So I have 2 sine and sine. Hopefully you're a little bit more comfortable with factoring the trig functions than you were last unit. I think hopefully we're good. So I know this has to be a 1 and a 1. So my back sign is negative. That means my signs have to be opposite, and I need to place them to where my result is positive. So here looks like that would work. So let's check it out. 2, yeah, that's right. So that's my proper factoring. Now I'm going to go back to a theorem that we learned in algebra. You may or may not remember it. The theorem tells us that if I'm multiplying two things together and I get a 0, that means one of them has to be a 0. Right? It's impossible. It's not. If I'm multiplying two things together and I get a 0, one has to be 0. So what I'm allowed to do is I'm allowed to set each of these factors equal to 0 and solve. So I would have 2 sine x minus 1 is 0, and then I would have sine x plus 1 is 0. Basically, this is going to be two strands of answers. I'm going to have solutions off of this strand and solutions off of this strand. I'm going to work them independently. So let's start with this one first. I would move the 1 over, divide by 2. So in this one I have sine x equals 1/2. So let's think unit circle. We need sine to be a half. Sine would be a half when it's low, right? When it's low because it's the smaller number. And there are two places where sine is positive. We have this location and this location. So we're going to have, two solutions for this strand. So let's think about this. What are we at? So at pi over 6, right? Pi over 6 would be where that was true in the first quadrant. In the second quadrant, what would that be? Do we remember? 5 pi over 6? Yep, you guys got it. 5 pi over 6. So, and what is the normal period for sine? 2 pi. So that's what I'm going to use in my solution. So x could be pi over 6 plus 2 pi n, or x could be 5 pi over 6 plus 2 pi n. So those are two of my solutions so far. So now let's work on the second strand, this one over here. I would move the 1 over, so I would get sine x is negative 1. And so that's only true in one spot in one rotation, isn't it? Down here. So sine being negative 1 would occur at 3 pi over 2. Right, so I would say x equals 3 pi over 2, again, plus 2 pi n, because that's the standard period for sine. So I have several solutions on this particular problem. Okay, how are we doing on that? We okay? Okay. Number 3, actually, it looks so innocent. So many students have trouble with this problem. They see something like this and they think, oh my gosh, I need to do an addition property or something like that. If it were secant 2 theta, you would want to do double angle property. Please don't do any of that. Okay? Please don't do any of that. And just think about, I'm going to show you the easiest way to solve one of these, the most straightforward. If you do those things and make the expression bigger and bigger, it is not going to be helpful. Okay, it's going to make it more difficult. So, now, first thing I would do, now this is my preference kind of thing. You do not have to do this. I really prefer cosine over secant. I know it probably hurts secant's feelings. I don't want to do that, but to be honest, I know cosine numbers way better in my head than secant numbers. So I would actually, and this again, you do not have to do this, I would change this to cosine theta plus 81 degrees equals 1/2. What I have just done is I've done the reciprocal of both sides of an equation, and that is a thing that you are allowed to do. That's an okay thing. The reciprocals are also equivalent. So that's okay, you can do that. Okay. So now what I encourage you to do is to just kind of put your hand over this part right here. Don't even look at it. Don't look at this part right here. Just whatever's in there, don't look at it. Think about, where is cosine 1/2? That's what I want you to think about. Where is cosine 1/2? And I'm going to go over here. Let's think about our unit circle. Cosine would be 1/2 when we were taller, right? Because that's a smaller x value. And we're in degrees. So this would be what, 60 degrees, or I actually prefer radians so much. I mean, I think maybe our heads are already in radians, aren't they? Oh, that's pi over 3, right? And who knew that we would be like that, right? Yeah, we fought about that for a while, but radians are better. At any rate, this is degrees. We have to go back to degrees. So we are at 60 degrees. Is there another place where cosine is 1/2? There is, isn't there? Down here. And so we can do, and actually I'll do the unit circle value. Well, what did I do on here? Yeah. I'm going to go ahead and just do a positive rotation. So if we go all the way around here, 270 and 30, so that's 300. Or we could do negative 60 degrees, it's fine. Either one of those is fine. So now that we have that, what we're going to do is we're going to take, so we know cosine is 1/2 at those two locations. Now we're going to take whatever we had inside here and we're going to set it equal to those two numbers. That's how this works. Way easier than trying to do some kind of a property to expand this thing to be gigantic. So now I know that theta plus 81 degrees is 60 degrees. I know that's one option. So I would solve that. I would move the 81 degrees over. And so 60 minus 81 is negative 21 degrees. And then I would, again, I would set this, basically the argument of cosine equal to the second one, which is 300 degrees. And then I would do the same, solve for theta. So theta equals, 300 minus 81, which is 219. Now when I'm writing the solution, I really have to pay attention to what my period is, because we know that the periods aren't always going to be standard, right? They're not. You need to watch for that. Don't always just automatically put down, 360 or 180 or whatever. Pay attention. So in this particular instance right here, what is cosine's period? It is 360 degrees, right? Do you remember what changes the period? Remember that number that goes right here? If there's a number there other than 1, the period's going to be different, so we need to pay attention to that. If this number is something other than 1, then you're not going to be writing plus 360. You're going to be writing something else. So I don't want you to miss out on that. That is another common place that I see mistakes. So let's go ahead and write our solutions. So theta could be negative 21 degrees plus 360 degrees in, or theta could be 219 degrees plus 360 degrees in. It doesn't matter to me whether you put the degrees on the 360 or on the in. I mean, it's just whatever. I usually write it like that. And that's our third one. We okay so far? Okay, the last one that we're going to look at, number 4. Come on, there's a squared there. So this one is a classic problem that I also see. See these little innocent cosecants over here, right here and here? I can't tell you how many hundreds of students divide it off and just ignore it. Okay, you potentially have lost half your solutions. Okay, I don't want you to be with the hundreds of students that do that. I want you to be with the thousands of students that don't do that. Okay, don't do that. Do not divide off the cosecant or whatever it happens to you. If that was sine, cotangent squared equals sine, don't divide off the sine, because what you will have just done is erased half your answers and half of the points on the problem. Please don't do that. Instead, we always keep it, move it to one side, and factor. That's what we do. I mean, there's going to be a GCF, right? That's the same thing on both sides. So I'm going to keep it. I'm going to move it to the other side. So I have cosecant, cotangent, minus cosecant equals 0. That's what I need to do in situations like this. I do not ever cross them off and get rid of them. Okay, no chopping them off. All right. So we would do a GCF. We would factor out the cosecant. So cosecant times cotangent squared minus 1. Now I use my property where I'm going to take each of these and set them equal to 0. So cosecant x is 0 and cotangent squared minus 1 is 0. Okay, so we have 2 strands of solutions to work through. Now with our knowledge of cosecant squared, is it possible for it to ever be 0? No. So I can actually just cross that strand out. That is not viable. That's unusual for a problem like this. Normally there are solutions there and you would have lost. I mean, I still need to see it and to see it crossed out there. We never are going to divide them and get rid of them. Okay. So then I'm going to work on this. So then I have cotangent squared equals 1. So I square root both sides. And I have cotangent x equals, what is it going to equal? Plus or minus 1. Right? What is the standard period for cotangent? Just pi. It's just pi, right? So we need to think unit circle. I'll just kind of go up here. We know we need the positive and negative version of it. You know, the positive, and we'll just go here for negative because that's where cotangent normally is. It's its principal value. So where are we at? Pi over 4, right? So x could be pi over 4 plus pi n. And what about this location here where cotangent is negative? That would be 3 pi over 4, right? Or x could be 3 pi over 4 plus pi n. Great. I actually want to talk to you about one other scenario that has to do with this dividing off thing. Let me show you. So what if I had sine equals cosine? Okay, in this instance it is okay to divide because I'm not, so let me show you what I'm going to do and then I'll explain why it's okay. I'm going to divide both sides by cosine. And that's going to give me tangent x equals 1. So the difference is, did I just chop off the cosine and ignore it? No, I incorporated it into the sine and I turned it into another trig function. That's okay. That's really one of the only ways I can solve this problem, right? How else am I going to solve it? I can't move the cosine over and, I mean, you know, the This is one of the only ways I can solve it. And so this is what I would solve instead of that. So that kind of division is okay. But the division here where I would just divide the cosecant over and chop it off, that's not okay. Does that make sense? Because students are usually confused. Well, I thought you said we couldn't divide. Okay. So yes, this is okay division. This one would not be okay division. Okay? All right.